All right, a very warm welcome, everyone. This is AEFAC's first webinar from the What's New in AS 5216 webinar series. A few housekeeping notes. You'll be able to use the chat function, as some of you may have already realized. So any questions or comments that you have, please type them in the chat box, and we'll have a Q&A session after our speakers have ended their presentation. So this session is being recorded, and the recording will be made available on the AEFAC website. PDF slides will also be made available. After this webinar, you'll receive a follow-up email. We'll ask you for your feedback, so we would really appreciate any feedback that you can give us to help us improve our webinar series. And also, if there are any topics of interest to you, please feel free to nominate as well, so that we can incorporate in our next webinar. Someone has their hands raised up. As well, so is that a question? Please feel free to type in the chat room, and then we'll attend to your question after the presentation. Thank you. Right, my name is Jessie. I'm your moderator for this afternoon. I'm AEFAC's Training and Development Manager, and I'm also a Senior Lecturer at Swinburne. So today we have two speakers, Dr. Anita Amir-Sadari and Dr. Tilak Pokharel, who will present the new edition of Seismic Design and Pre-Qualification in AS 5216. Our first speaker for this afternoon is Dr. Anita Amir-Sadari, who is a research fellow at Swinburne. Anita received her PhD from the University of Melbourne, specializing in earthquake and structures. Anita is a working group member of AS 5216 committee and is one of the main drivers for the development of seismic in AS 5216. And our second speaker this afternoon is Dr. Tilak Pokharel, who is AEFAC's National Technical Manager. His role within AEFAC is to develop technical resources for the fastening industry. Tilak is a member of Standards Australia Committee ME29 for fastenings and is the drafting leader for AS 5216 2021 revision. Tilak is also a member of the FIP Task Group TG 2.9 for fastenings to structural concrete and masonry. Right. So before we start, I'd like to bring your attention to three critical elements that are important for quality assurance of fastenings. So number one, there it is coming up, pre-qualification. So an anchor product must be independently tested and assessed to be fit for purpose. For examples, anchors that are to be used for seismic applications must undergo a separate series of tests to meet the requirements to perform under seismic conditions. Number two, robust design is required to ensure that all possible failure modes have been considered and the anchor is designed for the critical failure mode. Now, the third element that is important for quality assurance is installation, which tends to be the weak link. Many failures have occurred in the past due to poor installation practices. So all these three elements are critical to ensure that we have good quality assurance for the fastening. So a bit of introduction to AEFAC. AEFAC is a non-for-profit industry initiative founded in 2012 by Swinburne University and 6 other industry partners, as you can see on the slide, DeWalt, Hilti, Hobson, Leviat, Ramsat, and Worth, to introduce governance to the anchor industry based on the three critical elements for quality assurance that we have just visited earlier. Now, prior to the formation of AEFAC, the industry was fragmented. There was no uniformity or consistency in terms of anchors pre-qualification, specification, design, or testing. And AEFAC has since grown. There are currently 13 industry members contributing to the work done by AEFAC. Now, AEFAC contributes to various sectors in the anchor industry to uplift safety, quality, and efficiency. For designers, AEFAC provide guidelines for design and specification of anchors. For contractors, AEFAC provide training and certification for installation of anchors. For field engineers, guidelines are provided for field testing of anchors on site. For manufacturers, guidance are provided for minimum performance required for anchors in safety critical applications. And lastly, at Swinburne, we are continuing to do many R&D in various research areas, such as performance of anchors in early age concrete, seismic, and other types of innovative concrete. And also timber. I'd like to introduce the AEFAC Installer Certification Program. Now, as we know, if an anchor is not installed correctly, it will not perform as intended. So it doesn't matter if you have the best anchor product in the world, if it's not installed properly, it will not deliver what it's intended to do. Right, the AEFAC Installer Program is to train and assess installers' competency in installing post-installed anchors according to manufacturer's installation instructions. This program has been referenced in various Australian standards and road authority specifications such as Vic Roads Section 680. For safety critical applications, it is recommended for engineers to specify that the anchors should be installed by a competent installer under appropriate supervision. Without proper installation, the anchor will not perform as intended, which may lead to premature failure. Please visit the aefac.com/ICP website. There are free online training provided and also installation videos. So AEFAC instigated the development of TS 101 in 2015, which is the first deemed to satisfy guidelines for design of anchors in concrete. And TS 101 was then developed into a full Australian standard, AS 5216, in 2018. And this year, the new version of 5216 is published. So AS 5216 covers the design of post-installed anchors and anchor channel. However, the items that are listed in red was not covered in the 2018 version. In the latest revision in 2021, we have now covered items for seismic, anchor channel in three-dimensional loading, post-installed rebar connections, and redundant non-structural connections. There will be other webinars coming up to cover the other topics, but for today, we are looking at design for seismic actions. Last note, AEFAC has published many technical notes on various topics, so please feel free to visit the AEFAC website. All our technical notes are free to download. And without further ado, I'd like to invite Dr. Anita Amir-Sadari to present our first topic for this afternoon.
All right, thank you, Jessie. All right, so today I will be talking about seismic pre-qualification requirements for fasteners, which has now been included in AS 5216. So this is the outline of my presentation for today. I'll start off by talking a little bit about the seismicity of Australia. Then I'll provide an overview of the seismic provisions which have been added to AS 5216. And then I'll go through the details of seismic pre-qualification requirements for fasteners and the background work that was undertaken to develop the criteria in AS 5216 for selecting the level of seismic pre-qualification required for fasteners. So starting with the seismicity of Australia. As most of you know, Australia is considered to be a low to moderate seismic region, and I'm just going to play this video here from Geoscience Australia, which is showing the significant earthquakes that have happened in Australia since 1964. We can see that Australia does experience frequent earthquakes, even though it is typically considered to be tectonically stable. Australia is actually one of the most active intraplate regions in the world, as it's in compression due to the Indo-Australian plate moving towards the Eurasian and Pacific plates. As stated by Geoscience Australia, Australia is subjected to earthquakes which are of magnitude 5 or greater on average every 1 to 2 years, and earthquakes which are above magnitude 6 occur about once every 10 years. This is the current seismic hazard map, which is in the Australian Earthquake Loading Standard, AS 1170.4. One key challenge with Australia is predicting where earthquakes can take place, and that's why since 2018, the standard has specified minimum hazard levels for different return period events defined by the variables K, P, and Z. So now the minimum hazard design factor to be considered for a 500-year return period event is set to 0.08. I'd like to also highlight that in the past we have seen significant damage caused by relatively moderate magnitude earthquakes. One of the most damaging and costly earthquake was the 1989 Newcastle earthquake, which was a magnitude 5.6. It caused 13 fatalities, 160 serious injuries, and it resulted in 50,000 buildings being damaged and around 300 buildings which required to be demolished. We've had larger magnitude earthquakes as well, but due to the fact that most of them have happened in remote locations, the damage caused by these earthquakes have not been as great as the Newcastle earthquake. Now, for those of you in Victoria, a couple of weeks ago, you would have experienced some shaking. So on September 22nd, Victoria had the largest earthquake that has been recorded. It was a magnitude 5.9 earthquake near Woods Point, which is approximately 130 kilometres east of Melbourne. The earthquake event as experienced in Melbourne was less than 20% of the design event for most buildings. So for this size of an event, it was expected that buildings would have responded within their elastic range and that we would have minimal damage, and this was generally observed all throughout Melbourne. In general, the most vulnerable buildings to earthquakes are unreinforced masonry buildings, which can fail at lower earthquake events, and an example of this was seen with one of the buildings on Chapel Street. So now I'll move on to discussing the seismic provisions that have been added in the 2021 version of AS 5216. So the design requirements for seismic actions have been included in Appendix F of the standard, and I've just highlighted the clauses that you will find in that appendix. In terms of the scope, it needs to be considered for structural and non-structural elements that need to be designed for earthquake actions in accordance with AS 1170.4. And the scope currently covers post-installed fasteners located in regions of concrete members where concrete spalling or yielding of reinforcement is not expected to take place. And I'll talk a little bit more about this point later on. The standard describes the pre-qualification requirements in Clause F3, and the design requirements are provided in Clause F4 to F7, and you'll see that reference is provided to the AEFAC technical note for design, and you can find the technical note on the AEFAC website. My presentation today will focus on the pre-qualification requirements, and then Tilak will discuss the design requirements. So moving on to looking at the seismic pre-qualification requirements for fasteners. Generally speaking, fasteners don't have predictable capacities for all failure modes, and therefore they require pre-qualification, which involves a series of tests and assessment procedures to define their performance. Different pre-qualification is required based on the intended use of the fastener. The pre-qualification requirements are provided in AS 5216, which refer to European assessment documents or technical reports. There are 4 levels of pre-qualification. The first 2 are for cracked and uncracked concrete, and these include tests that are conducted for reliability and service conditions of the concrete substrate. For cracked concrete, the fasteners are tested in approximately 0.3 mm crack widths. These requirements are covered in the 2018 version of AS 5216. Now, the other 2 levels of pre-qualification are for seismic conditions, and they're referred to as Seismic Performance Category 1 and 2, or simply C1 and C2. And these are now included in the 2021 version of AS 5216. The seismic pre-qualifications are based on European practice, which are provided in the Technical Report 49 by Eurocode, the European Organisation for Technical Assessment. For C1 category, the fasteners are installed in a crack which is open to 0.5 mm. Then the fasteners are subjected to pulsating tension and alternating shear loads. The crack width is kept constant throughout the test, and the fasteners are not allowed to fail at a specified load and number of cycles. If they do fail, then the test must be repeated at a reduced load. For C2 category, similar tests are conducted as for C1. However, the cracks are opened to 0.8 mm during cyclic load tests. And there's also an additional crack cycling test where the crack is opened and closed under tensile load. And this is done to simulate the effect of moment reversals that may be experienced by a structural member. I'd like to also note that similar pre-qualification requirements also exist in the United States. However, they currently only have 1 seismic performance category, which is equivalent to C1, but they're also in the process of introducing a 2nd category, which will be similar to C2. So the seismic pre-qualification requirements that are discussed today all assume that the fasteners are located outside of regions where yielding of reinforcement and spalling of concrete may occur. So if we're looking at flexural members, this means that it's outside of plastic hinge regions. And this is reflected by the conditions under which the pre-qualification tests are undertaken, including the maximum crack width limit of 0.8 mm, which is based on studies that have shown that at yield, the upper bound estimate of the crack width is around 0.8 mm. So having the different levels of pre-qualification leads to the question, what level of pre-qualification is required for fasteners designed to resist seismic actions? And to answer this question, we first reviewed international practice to see what type of selection criteria is adopted. And that takes us to the 4th item for this presentation. And I'll just briefly go through some of the selection criteria that we see in international standards. So these are the requirements in Eurocode, which specify the level of pre-qualification required for fasteners designed for seismic actions. I won't go through the details of the criteria, but what we can see is that the selection is based on the level of seismicity, the local site conditions, the importance level of the building, and also for some cases a distinction is made based on whether the fasteners are used in structural or non-structural connections. These are the requirements in the German annex to the Eurocode. So their approach is quite different to Eurocode. It's directly based on the expected crack widths of the concrete substrate, where the level of pre-qualification coincides with the maximum crack widths required for the pre-qualification tests. However, since it's not always practical or feasible to calculate the crack widths, they also use the behaviour factor to approximate the expected crack widths. Now, the behaviour factor is a parameter that is used in design which accounts for the level of intended inelastic response of the structure. It is equivalent to the ductility factor divided by the structural performance factor in accordance with the Australian practice for seismic design. In the United States, the fasteners need to have seismic pre-qualification based on the seismic design category of the structure, and these are assigned based on seismicity, local site conditions, and risk category. Also, with the introduction of the second seismic performance category, it is likely that this selection criteria will be extended, and it may incorporate a structural response parameter. So what we can see is that in general, there's no consensus on the parameters or limits that have been used to define selection criteria in different standards. Each country or region has adopted a method that's suitable for their own seismicity, design, and construction practice. But in general, we can see that they have considered one or more parameters related to seismic design, design of the structure, seismic demand, and also the consequence of failure of the structure. So the question that remained was, what is suitable for Australia? And to help us answer that question, we first undertook rapid assessment of buildings in Australia. So the approach that was adopted used displacement-based principles instead of force-based principles, which are typically used in design. And the advantage of using a displacement-based approach is that the focus is on deformation demand, which can then be more directly related to the damaged state of the building and its components. And this assists with determining the level of pre-qualification that is required for the fasteners. This is an overview of the assessment approach that was adopted to approximate the seismic displacement and drift demand on a building, which used existing models in the literature. Different types of buildings, including worst-case scenario type of buildings with planned asymmetry, were considered for a range of earthquake intensities and different site conditions. Then we set limits to the interstory drifts for which the different seismic performance categories are likely to be suitable. And to develop these limits, we looked at interstory drift that is likely to correspond to initial yield of flexural members, experimental results for the progression of crack widths and drift demand, and expected ultimate drift capacity of the building components. And what we concluded was that for drifts less than 0.5%, seismic pre-qualification of the fasteners is not required. For drifts between 0.5 and 1%, C1 category was necessary, and then for drifts greater than 1%, we suggested C2 category. We then plotted the expected maximum interstory drifts for various buildings considered, so buildings with various heights, and for a range of seismic intensities and site conditions, which was defined by using the parameters in the Australian Earthquake Loading Standard, including KP, the probability factor, Z, the hazard design factor, and FV, the site amplification factor in the velocity control region. And this can be calculated from the response spectra provided in AS 1170.4 for the various site conditions. And by looking at the 95th percentile of the results obtained, we looked at the limits at which the 0.5% and 1% drift were reached. So the limits from the previous graph were then used as a guide to develop this table here, where essentially the limits obtained from the analysis are directly adopted for importance level 2 buildings. And then for importance level 3 and 4 buildings, the minimum level of pre-qualification is set to C1 and C2 respectively. And this is because the failure of connection in these high importance level will have greater consequences. Also, you'll notice that seismic pre-qualification is not defined for importance level 1 buildings, and this is because AS 1170.4 does not require seismic design of these structures. So essentially, we've ended up with a table that is similar to Eurocode, but it's based on what we expect to be suitable for Australian conditions. We have also not set separate requirements for structural and non-structural connections. And this is because if a connection is safety critical, then the failure of the connection can be equally severe. So now I'll go through the selection criteria that you'll find in AS 5216. You'll notice that we've included 2 criteria for determining the seismic performance category required for the fasteners. So we've provided one criteria which is referred to as a normative requirement, and then another which is referred to as an informative requirement. So this is the table in AS 5216 that we've included as an informative requirement. It is essentially the same table that I showed previously as a result of the rapid assessment. However, instead of showing the site amplification factors, we've specified the requirements for each site class separately, and this is just to make sure that the way the information is presented is consistent in format with AS 1170.4. We have suggested this table to be incorporated in the standard as an informative requirement, or you may view it like a deemed to satisfied approach when detailed analyses are not undertaken to examine the structural response under seismic actions and the extent of damage that is expected to the concrete substrate. For the normative requirement, we have suggested this table where the suitable seismic performance category can be directly selected based on the expected level of damage to the concrete in which the fasteners are to be installed. And this can be achieved by calculating the expected crack widths under seismic actions and considering the opening and closing nature of the cracks. So we've put this table as a normative requirement since it's directly in line with how the pre-qualification tests are undertaken, and you'll notice that it's also consistent with the normative type of requirements that are specified in the German annex. I'd also like to go through a couple of examples which show the seismic performance category that's required for fasteners for different buildings, and we've done a comparison by using both the Australian selection criteria and some of the international standards. So as an example, I'm showing here the requirements for an importance level 2 and 3 building in Australia on a site with a design hazard factor of 0.08 and a mu on SP of 2.6, which is what usually buildings are designed with. The green bars are showing the requirements based on the Australian informative requirement. The blue bars are the recommendations in accordance with US standards. Red is in accordance with Eurocode, and the yellow is showing the requirements based on the German annex using the simple method, which is based on the behaviour factor. For the buildings that are considered here, we can see that in general the most stringent requirements end up being those by the German annex. And this is because with the simplified approach, C2 is recommended for a behaviour factor that is greater than 1.5. The second most stringent requirements tend to be by Eurocode, and the least stringent are those by the United States. However, the US has not incorporated the C2 type of category pre-qualification for the fasteners in their standards. In terms of Australia, we can see that the requirements fall somewhere in between European and US requirements. And this is another example for an importance level 4 building. And we can see that essentially all the codes are recommending the C2 pre-qualification, except for the United States, which hasn't incorporated the C2 in their recommendations at this stage. And before I end, I'll just go through some conclusions. So I've provided a brief overview of the study that's been undertaken to develop the criteria for selecting suitable seismic performance categories for fasteners in Australia. Two forms of criteria have been provided in AS 5216. One is a normative requirement, which involves assessment of the structures to determine the expected level of damage to the concrete substrate. And the other is an informative requirement, where the level of pre-qualification is determined based on seismicity, local site conditions, and importance level of the building. Thank you for your attention. I'll pass it on to Tilak now, who will talk about the design requirements.
Thank you, Anita, for covering the pre-qualification part, and I will be talking about the design part. So before starting the design requirement, I'll start with the scope and limitation of the standard. So the current requirement given in AS 5216 2021 is only for post-installed rebar connections. And there is a requirement for the low seismic region. For example, if seismic design tension force in a fastener or group of fasteners is less than or equal to 20% of the design force, that combinations, some of the section in the standard can be omitted. And standard fasteners with grout layer more than 0.5 times the diameter of the fasteners is not covered by the standard. Similarly, the fastenings for redundant non-structural applications are not covered. The standard assumes that the loosening of nuts and screw is prevented throughout the life of the connections. And finally, it doesn't cover the fastenings in plastic hinge regions. For the provisions, the design of connections for the transmission of earthquake loads is carried out in accordance with Appendix F of the standard, as Anita mentioned before, and the design value of the seismic actions determined in accordance with 1170.4. And there is a distinction in the standard on the design options depending upon the ductility requirement of the connections. Accordingly, there are three design options given in the standard. Option 1A and 1B are for those conditions where there is no ductility requirement in the connections or due to the fasteners, and option 2 is used where the ductility requirement of the fasteners is considered. So let's talk a little bit more about those design options. Let's start with the first one, capacity design. So the connections are designed for the maximum stress that can be reached when the ductile failure of the component to be connected. And the fasteners will within the load limit, and there is no damage in the fasteners. Option B is elastic design options, and the connections are designed for the maximum seismic actions, assuming an elastic behavior of structure as well as the elastic behavior of fasteners. And option 2, which consider the ductility of the fasteners, the design should consider the ductility along with the yield strength and deformation capabilities of the fasteners is considered properly. There are some requirements to be used for all the options, option 1 and B, and we have covered those requirements in the presentation so far, but I'll just like to highlight them again because they are relatively important here. For the seismic design, the fasteners used must meet all the requirements from non-seismic conditions first. The C1 and C2 pre-qualification testing Anita just mentioned, they are on top of the requirement we have for non-seismic conditions. And only the fasteners for crack concrete needs to be used in this section of the standard, and connection within the hinge region is not covered, because in hinge region there would be yielding of reinforcement or spalling of concrete, and that will significantly reduce the capacity. In some cases there wouldn't be even concrete to hold the fasteners in place. So to design the fasteners using option A1, 1A, the capacity design method. The design is done for the maximum tensile and shear load, and the fasteners are designed at least for the load combinations in which ductile failure, ductile yield can formed in the member connected, or the fixer plate used to connect the member to the fasteners. So in this case, the strain hardening and material overstrength should be considered, and hence the load in the fasteners should remain reliably within the limit. And it's very important to note that the tension and associated shear force must be limited and superimposed accordingly during the design process. Option 1B is relatively easier, so it is designed for the maximum load obtained from the design load combinations that includes seismic actions corresponding to ultimate limit states, and we assume the structure as well as fasteners behave elastically throughout the life of the structure, and as we are doing the elastic design, the force is not reduced. That means SP over mu factor should be assumed as 1 during the derivation of the forces. And the seismic loading standard AS 1170.4 is used if you are designing the non-structural elements, non-structural connections. Section 8 of that standard is used. So the option 2, this is a little bit complicated, and there is no extensive applications experiences with this design option so far. So without additional detailed investigation, this application is recommended to be used for non-structural components only. So in this method, the fasteners are designed for maximum load obtained from design load combinations that include seismic action corresponding to ultimate limit states. And the fasteners should comply with seismic category C2, and the tensile steel capacity of the fasteners shall be smaller than the tensile capacity from concrete related failure, because we want to have ductile failure, and the concrete related failure are brittle, and we don't want that to happen. This option 2, the ductility method, applies to pure tension loads. Shear loads shall be carried by some other fastening elements. And depending on the applications, there could be some further requirements regarding elongations, ultimate length, and so on. And the fasteners shall not be used for the energy dissipation for the structure. If you want to consider that, more higher level of analysis, such as dynamic non-linear time history analysis, needs to be done. And more importantly, the historic behavior of the fasteners should be included in pre-qualification reports such as ETA. In option 2, the ductility method, the failure of fasteners steel element is very important. And to ensure that steel failure, there are actually 3 conditions given in the standard. The condition A is for the single fasteners used in tension. Option B is group of fasteners, and there is additional one option for the mechanical fasteners used to transmit the seismic actions. Actually, the tensile forces. To transmit tensile load, the fasteners need to be ductile, and there needs to be some stretching length which needs to be greater than or equal to 8 times diameter. The ductility requirement is given in AEFAC Technical Note 10, which is referenced in AS 5216. To have the fasteners ductile, the yield strength needs to be less than 800 megapascal, and the ratio of yield to ultimate should be less than 0.8. And there is some requirement in the elongation capacity of the fasteners as well. Regarding the stretch length, minimum stretch length 8 times the diameter should be provided either using anchor chair like this, or using some debonded material or debonded sleeve within the connection. For the forces, as I mentioned before, we use Australian seismic loading standard AS 1170.4 to get the forces in the connection. And if we are designing non-structural components, we use section 8 of that standard. If you don't have otherwise to prove, we use the maximum value of tension and shear forces, and we apply them simultaneously. And finally, the connection force is distributed to individual fasteners using the method given in section 4 of fastening standard AS 5216. Now let's look at the calculation of resistance. So this is the equation from the standard. We have RDEQ, and this RDEQ needs to be determined for loading, all possible loading directions, tensile loading, shear loading, or if there is any incline loading. And this value needs to be calculated for all possible failure modes, such as steel failure, pull-out failure, concrete spalling, pry out, any failure you have. And phi I in this equation represents the capacity reduction factor for that particular failure mode. And this value, the phi I value, should be calculated in accordance with Chapter 3 of AS 5216. And RKEQ in this right-hand side of the equation is the characteristic seismic resistance of a fastener. So now let's see how we calculate that value. So the characteristic seismic resistance is calculated from the basic seismic characteristics resistance, which is R0 KEQ. So if you compare these equations with the design equation for static loading, the resistance to seismic action is reduced by 2 factors, alpha gap and alpha EQ. The alpha gap factor takes into account the presence of annular gap between the fasteners and attached component or fixtures under shear loading. And the alpha EQ takes into account the various factors, including load distribution, uneven load distribution, and the crack associated with the uneven load distribution. I'll talk about the more detailed method on how to calculate R0 KEQ, but before that, let's see the factors, the annular gap factor, alpha gap. As I mentioned before, this is introduced in the standard to consider the effect of annular gap. It's not a detailed method to calculate the alpha gap value, but from the past experiments, we have seen that the fixer or the attached element hits the fastener if there is a cyclic loading, and we call that hammer effect, which will increase the load in the fasteners. But for the simplicity in this standard, this hammer effect is used to reduce the capacity of the fasteners rather than increase in load. So there is not a detailed analysis method that is available at this moment. We don't know the effect of gap length or number of cycle or type of material you are using. So we are recommending a simple method to get this alpha gap value. So if there is a gap, annular gap, we use 0.5 as alpha gap. And if there is no gap, or the gap between the fasteners and fixer element, we use alpha gap value as 1. If you want to use alpha gap equals 1, there are some requirements you need to meet. These are given in clause 4.2.2.1 in AS 5216. For example, if you have a fasteners which is welded on the fixer plate, alpha gap can be used as 1. If you have fasteners which is screwed on the fixer plate, you can use alpha gap equals 1. And it's sometimes we have seen that the gap or the hole clearance can be filled with appropriate method to increase the value of gap, alpha gap from 0.5 to alpha gap equals 1. And another factor, alpha EQ, that depends on the loading direction, loading type, and the failure mode you are considering. This value varies from 0.75 to 1, and this table is from the AEFAC technical note 10. And if we know the loading you are considering and the failure mode you are designing for, you can get alpha EQ factor for single fasteners or fasteners group. Now let's come back to R0K EQ. This is the basic characteristic seismic resistance, and this is calculated depending on failure mode you are considering and type of loading you are considering. For example, if you have a steel failure or pull-out failure under tension load, or shear failure under shear load, steel failure under shear load, these values are determined from the pre-qualification report prepared according to Appendix A of the AS5216, such as pre-qualification report ETA. And if you have a combined pull-out and a concrete failure in case of chemical anchors, the R0K EQ value is taken as NRKP, that's the pull-out capacity, with tau RK, the bond strength is replaced with seismic bond strength, tau RK EQ. And for other failure mode, relevant section of AS5216 needs to be used. And all the cases where the tau RK is used, this needs to be replaced with tau RK EQ to get the seismic resistance of the fasteners. For the verification of combined tension and shear forces, this needs to be carried out in accordance with Chapter 8 of AS5216. The separate verifications needs to be done for steel-related failure and concrete-related failure. And there are some additional provision to the Chapter 8 of this standard, which is given in the Appendix F of the standard. In addition to the requirement in terms of strength, in some application it is also required for the deformation or the displacement capacity of the fasteners needs to be verified. The displacement of the fasteners under tensile and shear loading must be limited on the basis of the requirement of the specific applications. The limiting displacement limits are application dependent, and the design engineer should be able to determine the allowable displacement in the analysis that is compatible with the requirement of the structure he is designing. So the standard specifies some initial guidelines if there is no detailed analysis for the limiting displacement. For example, if you have fixed connections, the limiting displacement can be taken as 3 millimeter. But it's always design engineers' call to limit that value. So the displacement of the fasteners, that's delta N and delta V for shear loading and tensile loading, is given in pre-qualification reports such as ETA, and if the specified deformation values are greater than the values required for the applications, the associated design value of the fasteners in tension and shear needs to be reduced in accordance with the equation you are seeing in the screen. Finally, to summarize this presentations, AS5216 has been recently revised, including 4 of the topics, and we covered the first one, Seismic Design of Post-Installed Fasteners. And as Jesse mentioned, we'll be having other webinars to cover some other topics as well. And seismic pre-qualification categories C1 and C2 has been introduced in AS5216, and there are 3 design options we discussed: ductility requirement and non-ductility requirement method. And for the design component, we covered strength requirement and displacement requirement for some high level or high importance structures. So before concluding, I'd like to thank AEFAC board and supporting members for supporting throughout the development of the standards and the drafting and all the process since the beginning. We also like to thank Professor Nelson Lam from the University of Melbourne, Professor Hingos and Scott from the Swinburne University of Technology. And we also like to thank Standard Australia Working Group and Standard Australia Committee, especially ME29. And without AEFAC Technical Committee's support, this would not have been possible. So we are happy to answer any questions if you have, or if you want us to contact for further information. We have email address in the list. The first one is AEFAC Central email address, second one is Anita's, and last one is mine.